Welcome to this presentation of our latest work, Quantifying Point Cloud Realism through Adversarially Learned Latent Representations. My name is Larissa and I conducted this research together with my co-authors David Peter, Stefan Baur, and my academic advisor Marius Zoellner. The aim of this work is to provide a method to estimate the level of realism for arbitrary LiDAR point clouds. We find this especially useful when working with synthetic data. For example, when synthesized with generative adversarial networks or simulation frameworks. Our literature review revealed a variety of different quality measures for images and generic single object point clouds. We discussed the aspects of these metrics in our paper and find that none of them can suitably define the realism for complex LiDAR scene point clouds. Since there is no unique definition to realism, we designed our metric to learn relevant realism features directly from distributions of real-world data. The output of the metric can then be interpreted as a distance measure between the input and the learned distribution in high-dimensional space. We define certain properties that we wish to see in a useful LiDAR metric. First, the realism score is a quantitative measure with well-defined lower and upper bounds. Then, the metric has to be applicable to any LiDAR input and therefore must be independent from any application or task. This means that we don't require any ground truth information. Further, the metric must give reliable and robust predictions for all inputs, independent on whether the data distribution of the input sample is known by the metric or not. This makes the metric transferable to new and unseen data. We also want the metric to be able to compute spatially local realism scores for smaller regions within a point cloud. It is also expected to focus on identifying the quality of the point cloud properties while ignoring global scene properties as much as possible. And finally, the metric has to be both permutation invariant to adequately handle unordered point sets and be fast to compute. We implement our metric in such a way that the described properties are fulfilled. The underlying idea of the metric design is to compute a distance measure between different data distributions of realistic and unrealistic LiDAR point cloud compositions. The network learns features indicating realism from data distributions. Specifically, the network is trained to classify point clouds from different data sets into 3 categories. The premise is the possibility to divide the probability space of LiDAR point clouds into those that derive from real data, those that derive from simulations, and all others such as distorted or randomized data. By acquiring the prior information about a tripartite data distribution, the metric does not require any target information or labels for inference. The architecture is based on hierarchical feature set learning, for which we use PointNet++. Query locations are sampled within the point cloud, from which then form local neighborhoods, and these neighborhoods are then individually processed by a PointNet model. We stack 2 of these abstraction modules on top of each other and obtain our feature representation per query location. Keeping the numbers of neighborhoods and abstraction level low limits the network to only encode information about local LiDAR-specific statistics instead of global scenery information. On the other hand, the high amount of query points helps to cover many different regions within the point cloud and guarantees the local aspect of our method. The features are then fed to a densely connected classifier, which outputs a probability score or a probability vector for each of the 3 categories for each neighborhood. The realism score for the entire scene is simply the mean over the probability scores of the real category, and for optimization we use a softmax cross-entropy loss. The setting so far does not ensure that the only realism relevant features are encoded and therefore does not satisfy our transferable property. Therefore, we want to actively enforce the feature extractor to not only encode dataset-specific information. To do so, we add an additional output head, the adversary, which is only required at training time. It is identical to the classifier and predicts the specific dataset where the input originates from. This again is optimized with a softmax cross-entropy loss. However, in contrast to the classifier, we reverse the gradient in the path between the adversary input and the feature extractor. Training with the reverse gradient results in the feature extractor encoding as little information as possible for predicting the dataset. This concept is adapted from fairness in machine learning to prevent networks from using sensitive information, and is also often used for domain losses. After successful training, we then obtain the following output. Here we see an example of a synthetic point cloud generated by the LiDAR simulator. The color shows the closeness to the respective category at discrete query locations, indicated by the gray circles. Local regions in the sample are largely predicted as being of synthetic origin. The next sample is from a real-world dataset, specifically the pandaset dataset. It is being predicted to be realistic. However, the special thing here is that the metric never saw any data from this dataset. For training, we only used KT and mu scenes in the real category. This shows the transferability of our metric to unseen data. On the bottom right, we see a sample generated by a generative adversarial network. It has large areas with high distortion levels that neither appear realistic nor synthetic. In one of our experiments, we compared different traditional and deep learning-based methods for LiDAR point cloud upsampling, shown on the y-axis of the figure. The right values show the realism score of our metric, while the left side shows the baseline metrics. In general, the baseline methods show a trend, but no clear correlation to the degree of realism, while our metric orders the upsampling methods according to human visual judgment. Given the locality aspect of our method, we are able to find anomalies or a region with differing appearance within a single scan. Here we see 3 examples where our metric outputs low real scores for real-world point clouds. All of these scenarios are rather uncommon to see in the data distribution, and therefore it might be interesting to automatically retrieve them from a large set of data for further inspection or labeling. We conducted more experiments to prove the soundness of our metric, including ablations on the adversary module and investigations on feature continuity. These and additional quantitative results can be found in our paper or on our project page. Thank you for listening. Please visit our project page and contact me in case of questions regarding our work.